Hi everyone, so let's see trends in melting point. So melting point of elements can be found in section 7 of the data booklet. So here you can see part of that section and you see the melting point is given over here and the boiling point is given over here. So all these values correspond to melting point and boiling points. Now, when we're talking about melting point, for you to melt an element, you need to break forces of attraction between the particles. So the value of the melting point will depend on the type of bond or the type of attraction between molecules or between the atoms. If you look at elements in group 1, so for your syllabus, we'll be looking at the trend in group 1 and in group 17. So if you look at elements in group 1 are metals, and you see that the melting points, all of them are high melting points. So metals have metallic bonds. So if you still remember that in metals, we have metallic bonds, and metallic bonds are formed when the metal is going to lose the valence electrons. So let's take, for example, lithium. So then you'll have the cation lithium that is going to be formed when the lithium atom loses the valence electrons. So you will have the cations in a sea of delocalized electron. Then you have the attraction between the cations, which is positively charged, and the delocalized electron, which is negatively charged. So you have an electrostatic force of attraction between these particles. This is what makes the metallic bond. So the stronger the metallic bond, which means that the more easily you have delocalized electrons, so the stronger the electrostatic force of attraction, which means that the greater the contact between the cation and the delocalized electron, the greater will be that force and the greater will be the melting point. If you look at all the elements in group 1, so what happens down the group, so you have the ionic radius is going to increase down the group. So when the ionic radius increases, what happens is that there is less and less contact between the cation and the delocalized electron, which means that the electrostatic forces of attraction is going to be less. So as the ionic radius increases down the group, the charge density decreases. What is the charge density? So the positive charge is concentrated in the nucleus. So the bigger the radius, the less that charge is able to attract something else, because there's kind of that shielding effect that we were talking about. So the smaller it is, the higher the charge density, which means that you have a small charge which is distributed over a small area, while in a big radius like over here, you have a charge that is distributed over a very large area, and that charge is less able to attract negative charges. So charge density, we say that charge density decreases, hence electrostatic force is going to decrease. So attraction between the cations and the delocalized electrons is going to decrease, and all of this is going to lead to a decrease in, so down the group we'll have a decrease in melting point. So this is going to happen down the group. The melting point is going to decrease. Let's see in group 7 now. So that was in group 1. Let's see in group 7. So in group 7, the particles are held to each other in strong covalent bonds. So this is intermolecular bonding. And this is a very strong bond. So you have covalent bonds, and this is because in group 17, the elements are bonded to each other. So you have diatomic molecules. So all group 17 elements exist as diatomic molecules. But when we're talking about melting, we are not breaking these covalent bonds, which means that we are not breaking any strong bond when we are melting or boiling a group 17, so group 17 molecules. But what we are breaking is the interaction between the molecules, because if we break these bonds, these covalent bonds, it's not going to be molecules anymore, it's going to be atoms. So we are not atomizing, we are melting, which means that we need to keep the molecule, but we need to separate the molecules from each other. So here in black, you'll see that these are the interactions that we are trying to break. So these are called intermolecular forces. I had made a mistake. So the one that is in between is intramolecular. It's inside the molecule, the interior bond. But the one that is the exterior bond is the intermolecular forces. And these intermolecular forces are weak forces. They are much weaker than covalent bonds or electrostatic forces, very, very weak forces. And these are the forces that we are aiming to break during melting. So we are going to break these bonds and separate the particles, the molecules, so that they are further apart from each other, so that you end up with a gas or a liquid. And these forces, the intermolecular forces, they depend on the number of electrons that is in the molecule. So, which means that the more electrons you have, the stronger these intermolecular forces is going to be, and the higher is going to be the melting point. So, if you look at down group 17, so down the group, the molecular size increase. So as you can see, the molecules become larger, bigger. Of course, it's going to become bigger because there is more electrons, so there's more shells. So number of electrons increase, molecular size, molecular mass also increases. And when this happens, the strength of London dispersion forces will increase. What are London dispersion forces? It's these intermolecular forces, these weak forces. These are called London dispersion forces. So London dispersion forces, what you might have heard as being van der Waals forces in IGCSE. So we're going to go into more details in the next chapter about van der Waals forces and London dispersion forces. But here what is happening is that the London dispersion forces is increasing. This is the weak intermolecular forces of attraction that's increasing. That's going to lead to an increase in melting point or boiling point down the group. Right? So this is what happens in group 17. So for your syllabus, you will have to know what happens down the group 1. So down the group 1, you have a decrease in melting point because electrostatic forces are decreasing, charge density decreases, ionic radius increases. But down group 17, there is increase in melting point or boiling point because the strength of the weak London dispersion forces is increasing because the number of electrons is increasing and the molecular size is increasing. Now, you will see all these explanation given in detail over here. So you will have the explanation in words. Now, it says here that in group 17, the molecules are non-polar, and the attractive forces are weak London dispersion forces. It increases down the group as molecular size and mass increases, and melting point increases. Now, non-polar, what does non-polar mean? So if you look at a group 17 molecule, so let's say we look at ClCl. Remember when we were talking about electronegativity, where I said that electronegativity is the ability of an atom to pull electrons, pull a shared pair of electrons towards itself. So different elements in the periodic table have different electronegativity values. But if you look at here, chlorine, so if you look in the periodic table, you will see chlorine here, electronegativity value 3.2. So each one has electronegativity 3.2, which means that both of them are pulling electrons equally. So the electrons will lie exactly, the shared pair of electron will lie exactly at the center of the bond. So it's not being pulled by either one. So which means that there is going to be the overall charge distribution in that molecule is going to be 0. So you won't have a permanent delta plus and a delta minus. No, this will not happen. So there is no permanent distribution of kind of a charge that is formed. So this is why we say that it's non-polar, because there is no charge distribution in that molecule. Right? We're going to get into more details about this, but for now, just to tell you what does non-polar mean. And usually when you have a polar molecule, the weak interaction, the weak intermolecular forces are stronger. So if you have something like, let's say, water, H2O, so here you have a charge distribution. So oxygen is 3.4 and hydrogen is 2.2. So this is 2.2, this is 3.4. So this is a higher electronegativity, so it will pull electrons towards itself. So you will have delta minus here, and here you will have delta plus. And because it is a delta minus means it is a partial negative charge that develops. It's not a complete cation, it's not a complete anion, but it has a partial negative charge that develops over here, which means that it can attract, that oxygen will be able to kind of partially attract the hydrogen from another water molecule. So then you have like an interaction, an intermolecular interaction between the oxygen and the hydrogen. And that interaction, that weak force, it's still a weak force of interaction, but it's going to be stronger than what we have over here, because here there is no partial negative or positive charges. The molecules are non-polar. So this is what I mean by non-polar. Let's see the trends across period 3 now. So if you look at, let's break this down. We're going to analyze part by part. So let's look at the metals in the period 3. So sodium, magnesium, aluminium, what is happening? So here you have an increase in the charge. So Na plus, Mg2 plus, and Al 3 plus, these are metals, so they will form metallic bonding. And as you know, metallic bonding is due to electrostatic force of attraction between the cation and the delocalized electron. So the more charged the cation, the higher the electrostatic attraction. So this is why aluminium has a much higher melting point compared to magnesium and sodium. The higher the charge, the greater the electrostatic force of attraction between the cation and the delocalized electron, hence the higher the melting point. Now, if you look at these nonmetals now, nonmetals, they will have simple, usually like group 17 will have simple covalent structures. But if you look at silicon here, it has a giant covalent structure. So remember in IGCSE you did the diamond structure. So in silicon there is the giant covalent structure. So here for silicon you're not breaking any weak intermolecular forces, you're actually breaking the strong covalent bonds. So covalent bond is a very, very strong bond, so it's much stronger than the electrostatic forces of attraction between cations and anions. Here you have to separate electrons, so you're breaking covalent bonds. So this is why silicon has the highest melting point across that period. So very strong, giant covalent structure, macromolecular structure. But if you look at phosphorus, sulfur, chlorine, and argon, these have simple covalent structures. So phosphorus exists as P4. So in that molecule, you'll have 4 phosphorus atoms. Sulfur is S8. Chlorine is Cl2. Argon exists as argon itself. So because there's 4 atoms of phosphorus, here you have 8 atoms of sulfur, here you have 2 atoms of chlorine. So there is some disparity in the molecular size. So the higher the molecular size, the greater the London dispersion forces. So S8, you'll see that it has the highest melting point, the highest boiling point and the highest melting point among these 4 nonmetals. So it's because of the molecular size. Higher molecular size means more strong London dispersion forces. P4, that's higher than chlorine. Chlorine is so there is 2 particles of chlorine atom in 1 molecule here. So this is high. This is actually higher than for argon. So you can clearly see there is actually no trend because of the difference in the molecular size, but you can see how the molecular size is related to the melting point and the boiling point. So the higher the molecular size, the higher the melting point and the boiling point. Argon has the lowest among the 4 nonmetals here because it is atoms. So you're going to work the questions for melting points. Thank you. Bye-bye.